Okay, so all right. I want to introduce chapter 7 a little bit, and this is on hypothesis testing. Okay, and this stuff will not be on the midterm, but I want to kind of introduce us to some of these ideas here. Okay, and so with hypothesis testing, it's also part of statistical inference in that we only see a sample of data, and based on the data we want to answer questions about the population. Okay, and so let's say you're playing a game with a friend. Okay, it's just a very simple game. And all you're going to do is you're going to flip a coin, and basically if it turns out heads, you win. If it turns out tails, you lose. Okay, and you just play this a bunch of times. Okay, so you're playing a game with a friend. Okay, and so let's say and the game is just flip a coin. And heads, you win. Tails, you lose. Okay? And so let's say, for whatever reason, your friend is the one who gets to flip the coin. Okay? Your friend gets to flip the coin. Okay, so scenario 1. Okay, you play the game 10 times. Okay, and it lands heads 3 times. Okay, so your friend flips the coin 10 times, it lands heads 3 times, and it lands tails 7 times. Okay? Will you accuse your friend of cheating? No. You would just say, oh, I had a little bit of bad luck, right? Okay. I mean, is it possible that your friend was cheating? It's possible, but we look at this and we would say, we don't really have any reason to question our friend's integrity at this point. Okay? He could be cheating, right? He could be, like, we lost more than we didn't win as much as we would expect to under random chance. But it's not, this doesn't seem all that weird. Okay? So we only won 30% of the games, but it doesn't seem that weird. Okay? Okay. All right, scenario 2. Okay, you play the game 1,000 times. It lands heads. 300 times and tails. 700 times. Okay, at this point, do we feel like our friend is cheating?
A little bit.
Yeah, this seems very strange, right? Like if our friend is the one flipping the coin and it's supposed to be a fair coin, it seems like we shouldn't be getting results like this, right? This seems like I think I'm being taken advantage of here or something, right? So something definitely feels strange, right? So here again we've won only 30% of the games. Okay, and something feels fishy. Okay. Because we would say, you know, there's something nagging in the back of our head that says if our friend was flipping a fair coin, we should be getting 50% heads and 50% tails. We didn't get 50% heads. We got 30% heads. And this, it seems very strange, okay? So, so you know, we expect, so if the coin was fair, if the game was fair, we expect 500 heads and 500 tails. Okay, we only got 300 heads, and so we understand that there is random chance involved, so we wouldn't necessarily get exactly 500 heads and 500 tails, but to get only 300 heads seems to be a little extreme to us. Okay. Okay, and so we have a little bit of basic intuition here, where we say, hey, you know, these results don't quite match up with what I would expect if the game were being played fairly. Okay, whereas under scenario 1, you know, we would expect about 5 heads and 5 tails, but to only get 3 heads and 7 tails, because of random chance, we say, well, I could have just been a little bit unlucky, and we would just leave it at that. We wouldn't really say this is convincing proof that our friend is trying to trick us or something. And so this is kind of the idea behind statistical inference, or not statistical inference, behind hypothesis testing. Okay. With hypothesis testing, we say we set up a pair of hypotheses, and we say we're going to assume that one of these hypotheses is true, and if that hypothesis is true, what could my data look like under random chance? And then we would compare that to what we actually see, and then if what we see doesn't differ from what we expect very much, then we say, okay, that's fine. On the other hand, if what we see differs quite a bit from what we expect, then that would give us indication that maybe something strange is going on. Okay. And so, you know, at what point there's kind of this question of at what point do we say this is fishy enough for me to call out my friend? Okay, so if we played 1,000 games and we only won, and it landed heads only 300 times, it landed tails 700 times, I think we would be quite convinced that something strange is going on, and that this is not we are not just getting very unlucky, but that something something is happening. But would we do it at 100 games? Would we do it at 50 games? Would we do it at 200 games? There's this question of how much. And so to answer that, we bring into account our understanding of probability. Okay? So with hypothesis testing, we set up a pair of hypotheses. One is called the null hypothesis. Okay, and then the other is our alternative hypothesis. Okay, the null hypothesis, this is kind of our this is sometimes called the status quo. And generally this is, and we assume the null hypothesis is true. And then the alternative hypothesis is what must be true if the null hypothesis is false. Okay, so if this is what must be true if the null hypothesis is false. Okay, so we often in studies we often set up our hypotheses hoping to prove that the null hypothesis is false. Okay, so often okay. And so with our silly coin flip game example, our null hypothesis in both scenario 1 and scenario 2 will be that the null hypothesis will be that the game is fair, and specifically that the probability of getting heads is 0.5. Okay? And then the alternative hypothesis would be that the game is unfair, and specifically that the probability of getting heads through something strange that we don't understand is less than 0.5. Okay. And then we have our data. We have data. So for scenario 1, the data was 10 flips, 3 heads. Okay, scenario 2 was 1,000 flips, and we only got 300 heads. Okay, this is our data. And then we ask this question. We said, well, if we assume, I'm going to just copy this over to our next slide. and we just say, if we assume that the null hypothesis is true, okay, what is the probability that we observe data like ours or something more extreme? Okay. So we're going to say, if the game is being played fairly, what's the probability that I only get 3 heads out of 10 flips? Or if the game is being played fairly, what's the probability that I only get 300 heads out of 1,000 flips? Okay? So, so this probability is called the p-value. The p-value is the probability of observing our data or something more extreme if we assume that the null hypothesis is true. Okay. So, for scenario 1, our p-values effectively, okay, is the answer to this question. Let's assume that the game is played fairly. For argument's sake, let's assume the game is played fairly. What is the probability that that we get 3 heads out of 10 flips? Okay, and then if we think 3 heads out of 10 flips is odd, we would also find 2 heads out of 10 flips and 1 head and 0 heads out of 10 flips also to be odd, in that it seems like the game is rigged against us. Okay, so that's why we include this something more extreme. So we would say that we get 3 heads out of 10 flips and then or less, okay, or less. So we'll also include 0, 1, or 2 heads out of 1 or 2 heads out of 10 flips. Okay, and so can we figure this probability out? Huh?
Can we use R?
We can use R, but well, what is the operation we would do? Yeah, we would just do binomial, right? We would do binomial. N is 10, P is 0.5, and J is 0 through 3. Okay? So this is binomial with N is equal to 10, P is 0.5, and J is equal to 0, 1, 2, and 3. Okay? So we can fire up R and solve this. Okay? So we would just do P binom 3, 10, 0.5. Okay, and it says that happens with a probability 0.1719. Okay. So, anytime you play the game 10 times, there's about a 17% chance that you're going to get 3 or fewer heads. Okay? So we'd say, oh, I guess I was a little bit unlucky. Okay? So this is, this doesn't prove that the game was being played fairly, but this happens often enough where we're not ready to say, I feel like our friend is cheating. Okay? This happens often enough from bad luck alone. Okay? So this outcome happens 17% of the time from, quote, bad luck alone. Okay. Okay. On the other hand, with scenario 2, we can ask, let's assume the game is being played fairly. Okay. What is the probability that we win, only 300 games out of 1,000? Okay, and also anything less, 0 to 299 from bad luck alone. Okay, so again, this will be binomial. We could do a normal approximation, but we've got the computer, so we'll do binomial. N is 1,000, P is 0.5, and J will be 0 through 300. So I'm going to do P binom 300, 1,000, 0.5. Okay. And we get 8.8 times 10 to the negative 38. To the negative 38. So 10 to the negative 38. This is an astronomically small value. Okay. So the answer is, could I have gotten only 300 wins by bad luck alone? And the answer is, well, technically yes, but it is so it's like, it's like getting struck by lightning 50 times in a row or something. It's just not gonna happen. I think winning Powerball is only on the order of like 10 to the 7 or something like that, and this is 10 to the 38. So this is could I win only 300 out of 1,000 from bad luck alone? And the answer is, technically it's possible, but it's so incredibly unlikely. Technically, it's possible. It's not impossible. It's not 0. Okay? But it is incredibly, incredibly unlikely. Okay. 38 zeros ahead of this. I'm just trying to think what is even comparable. I can't think of it. Anything. How many? It would be like some, like, pick an atom. Like, I've randomly designated one of the atoms on Earth to be the winner atom. Okay, and you're gonna randomly pick an atom on Earth. And if you get that one, then you win. Now, could it happen? I guess, but it's not very likely to happen. Okay, but it is incredibly unlikely to happen. So so instead, rather than us saying, well, you know, I just got really unlucky, we're going to say, well, I don't imagine that I've gotten this unlucky, okay? And instead, probably my initial assumption that the game is being played fairly is wrong, okay? So, so we reject our belief or assumption that the game is being played fairly. Okay, and then we conclude that the game is somehow, quote, rigged against us. Okay. And so this is kind of the base idea of hypothesis testing. We start off with a pair of hypotheses, and then and we say, well, let's assume the null hypothesis is true. What is the probability of observing the data that we have if the null hypothesis were true? Okay, and that probability is the p-value, and what we decide is that if the resulting p-value is large, we say, well, the data we have could have happened from random chance. And on the other hand, if our p-value is very small, we say, well, the data we have, I'm ready to say it didn't happen by random chance, but rather my assumption was wrong. Okay, and so we have to draw kind of this arbitrary line somewhere that says, when do we say our p-value is large and when do we say our p-value is small? And that is our alpha level. So we have something called a significance level alpha. Okay. This is the quote cutoff between quote large p-values and small p-values. Okay, and so if the p-value ends up being greater than alpha, we will say our data could have been a result of random chance. Okay, and we will not reject the null hypothesis. So this was, we could have won only 3 games out of 10 from bad luck. Okay. And on the other hand, if the p-value is less than alpha, we will say that our data is not a result of random chance alone. Okay, and in that case, we do reject the null hypothesis, okay? And so here we would say, we do not believe the result of winning 300 games out of 1,000 was just a result of bad luck. Okay, so if our p-value ends up being large, we say, well, maybe the data we have was a result of random chance. And if our p-value ends up being small, we say, well, maybe our data is unlikely to have been a result of random chance, okay? And so, the choice of alpha is kind of arbitrary. The established kind of just by convention, we often use alpha equal to 5%. Okay. But you could use a bigger alpha or smaller alpha depending on what you decide. Okay. So that'll be it for just kind of introducing the topics of Chapter 7 for now. We'll definitely revisit this after the midterm, or the week following the midterm. I thought maybe I'll just do a quick review of, stuff from the class. Or if you guys have questions about anything, I'm happy to take those. Any topics in particular I should go over? Okay, so stuff we've covered. Okay. So we've covered, we started off with just kind of like statistics basics, right? So here we talked about experiments versus observational studies. We talked about sampling, and then samples versus population. Then we talked about descriptive statistics. Okay. So we had the mean and the median for measures of center. What are kind of the conceptual definitions of the mean and conceptual definition of the median?
Mean is like the average of all the values.
Okay, well, yeah, I mean, both of these are kind of the idea of what is average or what's the center. But we said the mean is the balance point. The mean is the balance point of our data, and the median is our
Center point?
halfway point. Halfway point, okay? Or yeah, I guess middle. Middle is fine. Okay, so balance point versus halfway point. Okay, and then we have, for measures of spread, we have the standard deviation. Or variance. And then we have the IQR, and we also have the range. Okay. Which of these numeric summaries are not influenced by extreme values, not influenced by outliers? The IQR is not influenced by outliers. What else? No, the range is, but the median is not. So the median and the IQR are not influenced by outliers. Okay, but all the other ones are. And these ones are measures of spread, right? We covered the empirical rule. You guys remember that? What's the empirical rule?
68% of the data will be
Yeah, so 68, 95, 99.7. This is within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean. Okay. And then we had a bunch of graphic displays. So we had, histograms, dot plots, and box plots. Okay, so make sure you can, well, it's a multiple choice exam, so I won't be asking you to construct any of these, but make sure you can look at them and make the appropriate conclusions or read them. Okay. Okay, and then, all right, and then we covered probability. We had probabilities of A or B, and we said that's what probability of A. Okay, then we got probability of we had tree diagrams. And then we might ask you something like, what is the probability? A given B or something like that, right? Things of that nature. So this was like the disease and testing positive example and stuff like that. Okay, so is that okay? Okay, we had random variables. And we said, y could take on little outcomes. And then we said, okay, well, the expected value, the mean mu, is the sum product of the outcomes and their associated probabilities. So I don't know. In the book there was like the example with the fish and the vertebrae, and then the standard deviation is the square distance from the mean times its respective probability, summed up and taken the square root of. Are we okay with this? Do we need examples of this? Are we okay? Okay, and then so we covered the binomial distribution. And we said something like if you got n, p, and j, the probability that you can get some value j is going to be n choose j, p to the j power times 1 minus p to the n minus j power. And the mean mu is going to be n times p, and the standard deviation for binomial. Okay, and then we have the normal distribution. We said z-scores. And so we would, so I could give you, I give a a score, like a measurement, let's say a height, and then you tell me, what percent is, what percent of the data is lower than the height. Or I could give a percentage you find, or percentile, maybe I should say. And you find the corresponding height. Is also okay? Okay. And we're just checking along here. And then, okay. And then we had the normal approximation to the binomial. And so, you know, if as long as n times p was greater than or equal to 10, and we can approximate the binomial with the normal. Okay, and then so we would have mu is equal to n times p. Sigma equal to the square root of n times p times 1 minus p. And then, you know, the continuity correction is plus or minus 1/2. Depending on the problem. Okay. All right, and then we had the central limit theorem. And we said that the distribution of y bar comes from a normal distribution where the mean is the population mean mu, and the standard deviation is sigma over the square root of n. Okay. And, you know, the shape of the population does not matter. As long as n is large enough. Okay, so n has to be, well, if the population is normal, any size n is fine. If the population is not normal, we recommend n being 25 or more. But in some extreme cases, you might need even a bigger n. Okay? Okay, and then we said, well, if we know that the distribution of y bar is centered around mu, we can apply that to confidence intervals. Yeah, of course.
So the square root of NP times N1 minus P. In the book, there's also the square root of P minus 1 minus P over N.
Uh-huh.
And the difference when we have to use those, it's like proportion. Do we not need to necessarily worry about that second one?
Yeah. I don't like the second one, so I don't use it. It's the difference between asking the question. I'm gonna pick 50 M&Ms out of the candy dish. Okay. What's the probability I get 10 red M&Ms or more? Okay. I could ask the same exact question and say, well, I've picked 50 red M&Ms. What's the probability that I get 20% red or more? Okay, those are basically the exact same question, but when it's percentages, the continuity correction gets all weird. Okay, with pieces of candy, it's always going to be plus or minus 0.5. Okay, if you're dealing with counts, it's always plus or minus 0.5. So if I want 10 or more, what's the probability I get 10 or more? Then my continuity correction tells me I would go down to 9.5 and take everything to the right. Okay. If I were dealing with percentages, there's no way to figure out what to do with the continuity correction. You say 20% or more, but then the continuity correction is not 19.5% or something. You have to think, okay, well, if I'm doing with pieces, I would go to 9.5, and so 9.5 turned back into a percentage is 19%, and then you would do 19% or more for the continuity correction. But because it just gets all weird, I don't like it. So if the question does say something like, what's the probability that you get 20% or more red M&Ms? I find it easier just to say, well, 20% red M&Ms, that's the same as 10 red M&M pieces, and then just deal with counts. And
that is P.
Yes.
And it's just the count, not the percentage. I think that's what I messed up. Yes, but okay. Right.
So yeah,
So
because
it's like the numeric value corresponds to the equation that you gave us, the NP times.
yeah. So I prefer dealing in counts. Yeah.
I do too.
Yeah. I think
Not worried
yeah. But I mean, they're essentially asking the same question.
Right.
And it's like, if you want to continue dealing with percentages, then use those other set of questions or equations. But the continuity correction gets all weird, and so that's why I don't like it. Yeah. Okay. So with confidence intervals, we said, okay, well, so we'll first create a confidence interval for mu. In the confidence interval for mu, in the center we put our best guess for mu, which is y bar. We go plus or minus t star times s over the square root of n. Okay? And we use degrees of freedom equal to n minus 1. Okay? And then today we talked about confidence interval for the quantity mu1 minus mu2. And in this case, in the center, we put y bar 1 minus y bar 2. We're going to use degrees of freedom equal to n1 plus n2 minus 2. Okay? And you can kind of see the parallels, right? For for mu, our current best guess of what this quantity is y bar, and we go plus or minus some critical value times the standard error. For mu1 minus mu2, our current best guess is y bar 1 minus y bar 2. We go plus or minus t star times our standard error. So they're just kind of expansions of each other, and that's that. Okay. Are there any questions? Okay. I think the exam is very fair. And I think the allotted time is enough, but it might feel like there's a little bit of pressure to work halfway quickly, okay? So
It's all multiple choice, right?
it's all multiple choice, yeah. Okay. All right. Then we'll end just a few minutes early today. So with that,
Can we